Okay, our last topic for today is protection of alcohols. So this will come up in synthesis problems where you want to use a Grignard reagent, but you can't because it's going to interfere with some other functional group that's present in one of your molecules. So for example, suppose you want to do a synthesis where you're taking a ketone and you are trying to add a Grignard reagent to this to turn it into a molecule that looks like this. So if you're thinking backwards about how you're going to form this carbon-carbon bond, 1, 2, 3 carbons here, 1, 2, 3 carbons here. So you would think, okay, I should cleave the molecule right there. And maybe the two reagents that I should start with, if I think backwards, would look like my ketone. And then this would be the Grignard reagent on the right side. So it would have to be something like, let's move it over here. BRMG, 3 carbons and an OH. So that seems like those would click together to make the product that we want. But the problem, which we just learned about in the last lesson, was that a Grignard reagent is a really strong base in addition to being a great nucleophile. And so that really strong base is going to start deprotonating all of those alcohols in your sample. Maybe not within the same molecule, but it'll find another molecule and pull a proton off of that alcohol. And so that's essentially going to kill your Grignard reagent, and your reaction's not going to work. So what we really would like to do this problem is to use something on this alcohol that we call a protecting group. We need to protect this alcohol. So the Grignard won't deprotonate it. Okay, this is the whole idea of protecting groups, and specifically we're going to protect an alcohol. The way we're going to do this is to turn it into some other functional group that Grignards don't react with. Then we'll run our Grignard reaction, and then we'll have to deprotect that group and form the original alcohol. So let's write out how we would do that. Okay, so before I form the Grignard reaction, I would want to start with a reagent that looks like this. And we already talked about if I added the magnesium right now, the Grignard reagent would deprotonate that alcohol. So I need to protect this alcohol first. So my first step is going to be a protection step, and I'm going to write this one in red. I need to protect my alcohol. There are lots of different reagents you can use to do this. There are hundreds, maybe even thousands of protecting groups that exist for alcohols. One of the most common ones is something called TMS. So the way we put this protecting group on is we use something called Tms Chloride, and the side product in this reaction is an HCl. So this is one of those reactions where we add a little bit of base. Triethylamine is often used. You could use pyridine, but what this is going to end up doing is it's going to put a protecting group on my alcohol. So this becomes O-TMS. So this is now a protected alcohol. It's not an alcohol functional group anymore. When we're all done here, I'll draw what TMS looks like, but it's actually, the S stands for silicon. So there's a bond between an oxygen and a silicon atom. And Grignard reagents don't react with those. There's no longer an acidic proton on there. So now I can turn this into a Grignard reagent. I can add my magnesium, just like you did in lab, to make your Grignard reagents. And so this alcohol is not going to react because it's protected as a TMS group. And now I can do my Grignard reaction. So the ketone I wanted to use in this example problem was acetone. Then I'll add a little water to do my workup. And remember that dot dot minus attacks the partial plus carbon. We end up forming an alcohol. So at the end of this reaction, we're going to have a product that looks like this. OH 1, 2, 3 carbons, 1, 2, 3 carbons, and then I still have this protected alcohol, this TMS group, OTMS. So now my last step is that I have to deprotect that alcohol. So here, I'm going to switch to blue to show the deprotection step. Deprotect. So every different type of protecting group usually has some sort of deprotection reagent that goes along with it. In the case of TMS, there are two really common ways of deprotecting the TMS. The most common, kind of most specific way is to use a reagent called TBAF. And I'll show you what the structure of that looks like in a minute. But the thing to note is that the F stands for a fluoride ion. Another option here, which is less specific, is to use acidic conditions. And you have to get the right concentration to remove the protecting group. But the thing with acidic conditions is it's not always, acid can do a lot of things to a lot of functional groups. Like if you have a double bond in your molecule, that could add across a double bond. So this is not always the best choice. If you want to use a really specific deprotecting group, you would want to use TBAF. But it's good to be aware that acid can remove your TMS protecting group. So you might accidentally do that if you're not careful. Anyway, whichever reagent you decide to use is going to remove the protecting group. And so now you're going to get the final product that you were looking for. This alcohol, nothing happened to that. But this alcohol will now be deprotected. Okay, so that is the overall scheme. What I want to do now is just draw out for you what the structures of these two compounds look like. I'm going to draw out what TMS chloride looks like, and I'm going to draw out what TBAF looks like, just so you know what they are. But in synthesis problems, we always write them with their abbreviations. Okay, so TMS chloride, the TMS stands for trimethylsilane. So it's got a silicon atom in the center. TMS equals trimethylsilane. And TMS chloride just has an extra chlorine on it. So if I draw it out, it's a silicon in the center. The silane is for silicon. Trimethyl means there are 3 methyl groups, CH3, CH3, CH3. And then before you add it to your alcohol, it's going to have a chloride on it. So when the alcohol actually adds to TMS, it kicks off the chlorine. So a protected alcohol looks like, if we were write out the whole thing without any abbreviations, we would have our, whatever our alkyl group is, the oxygen from the alcohol, and then instead of having a hydrogen on that alcohol, it's going to have the silicon with 3 methyl groups. Okay, so that's a protected alcohol, but for short, we always abbreviate that as our OTMS. Okay, so that, if I'm keeping with the color code, this is what the TMS in our above reaction looks like. And then the other abbreviation I used in the above reaction was TBAF. TBAF, this one stands for tetrabutyl ammonium fluoride. I'm just going to draw a picture of it. Ammonium means you have a nitrogen in the middle. Tetrabutyl means that you have these butyl groups around the nitrogen. 4 of them. And this is a plus. So this is just a big cation. The reactive part of this is the F minus. So this guy, let me write this in the blue. This one, the fluoride ion forms a strong bond with the silicon in TMS. So if the fluoride ion is introduced into a protected alcohol mixture, it's going to pull this silicon off of the oxygen, and then it'll get washed away as a side product. So that was our TBAF. Okay, so those are just what the big structures look like. But again, as long as you kind of remember the general idea, you can always write them as abbreviations in reactions. Okay, so let's try an example problem where we need to use a protecting group. So if we look at the worksheet, the one that was titled Grignard Reactions and Protecting Groups, I'm going to do 5A on this worksheet. So this would be a good time for you to pause the video, try this problem on your own, and then tune back in to see if you got the right answer. So in the meantime, I'm going to write out this problem. We have a benzene ring that's got a couple substituents on it. Our goal in this synthesis problem is to turn it into a benzene ring that's got an extra carbon and an OH group on it. Okay, so thinking backwards, retrosynthetically, if I look at this molecule here, I see that I have all the same carbons on the left, but then there's a new carbon right here. So it would make sense to form that carbon-carbon bond with a Grignard reaction. Also, because I have the bromine here, it would make a lot of sense to have my Grignard reagent be on the left side. So to have something like this. MgBr. And then on the right side, I'm adding one carbon, and that's where the OH is going to end up. So it would make sense for that side to be my carbonyl compound. So something like this. H and H. I'm only adding one carbon. Now, the problem with doing that, you might notice, is that you have an acidic proton over here. And as soon as you form a Grignard reagent, it's going to act like a really strong base, and it's going to find those OH protons and deprotonate them. And then that, in turn, destroys your Grignard reagent. So this is an excellent case for where we need to protect our OH group. This group here, we need to protect. Okay, so that would be my first step here. Before I can form the Grignard reagent, I'm going to add Tms chloride and a little triethylamine base. And that will protect my alcohol. So now I'm going to have TMSO, a protected alcohol. Oops, I dropped a carbon there. Let's put that back in. TMSO. Okay, now I can turn this into a Grignard reagent. And I'm going to put a few steps together here to save time. But first I would add my magnesium and form my Grignard reagent. Then I would have, let's make a little more room here. Then I'm going to add my carbonyl compound to do the Grignard reaction, and then I would add water to work up my Grignard reaction. So in the end of all this, let's make a little more space here. This side is my protected TMSO. Over here, I've now done a Grignard reaction. So I've got the alcohol and that extra carbon added. And then my last step is just to remove the protecting group. I still have that on there. And so if I just add some TBAF, that will remove the protecting group. Okay, let's try one more problem on the worksheet, 5B. So again, pause the video, take a few minutes to try this one on your own, and then tune back in. So 5B has an aldehyde. And we want to turn this into this molecule here. So as I'm thinking retrosynthetically, it looks like I have 1, 2, 3 carbons here, 1, 2, 3 carbons, but I need to form a carbon-carbon bond right here between this carbon and the benzene ring. So as I'm thinking backwards, let's see, maybe I'll do this in red. The pieces that I'm going to want, that benzene ring is going to have to be the Grignard reagent. MgBr. And then this piece over here, I'm going to have my carbonyl at that carbon. So I want something like that. And I can always worry about putting that double bond in at the end. I could do a dehydration or an elimination, something like that. So this piece looks exactly like what I'm starting with. But the problem is, if I use this Grignard reagent directly on this reagent, it's not just going to attack where I want it to attack, it's going to come over here and it's going to deprotonate that alcohol. So once again, we have a case where we need to protect our alcohol. I need to use a protecting group there. So in the forward direction, the first thing I'm going to do is to add Tms chloride and a little triethylamine. That's not going to do anything to my aldehyde, but it will protect my alcohol. So now I have OTMS. Remember again, this is an oxygen connected by a covalent bond to a silicon atom. And then it's got a bunch of methyl groups around it. So that's now protected. So then I can add my Grignard reagent. So my Grignard reagent, I'm just going to abbreviate it as phenyl magnesium bromide. That's a Grignard reagent you could buy. You don't have to make it yourself. And then after I do that, I'm going to have to add water to work up the reaction. And let's make a little room here now. So my Grignard reagent is going to add. It's going to attack this carbon here, which means that this carbonyl becomes an OH bond when that oxygen gets protonated. And I still have my OTMS, my protected alcohol. I don't want to deprotect this yet, because if I deprotect it now, I'm going to have an alcohol and they might start reacting in the same way. So it would make sense to form my double bond next. So in order to do that, I have an alcohol here. It's a secondary alcohol. There's only one place a double bond could form if I do a dehydration reaction. So that's the fastest way to get to the double bond. I'm going to do a dehydration reaction, and let's squeeze that in down here. So concentrated H2SO4. So that's the only dehydration product that can form. Now, it could be that these acidic conditions might remove the protecting group. Usually concentrated conditions are not going to do that, but we can make a note here if we're not sure. It may remove the TMS, and if it does, it's not a big deal because that's what we want to do in the next step anyway. But in the chance that it doesn't remove the TMS, then my last step would be to deprotect that alcohol. So I would throw in some TBAF. That's going to do the deprotection step. And we've got our OH. And there's that molecule that we were trying to make in the first place. Okay, letter C, I'm going to leave for another video because we don't want this video to be too long. So that will be it for protection of alcohols. You can try 5C on your own and tune into the next video to check your answer.